KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class, we start to discuss with the topic heat transfer. Heat transfer, okay, right. So we all know very well, heat is a form of energy which flows from a body at high temperature to a body at low temperature, okay, right. So whatever it may be, whether it is from system to surroundings or from surroundings to system or within the system, right. For example, if you see the whole universe, right, which is what the unimaginable space in our surroundings, you know, we have different, that is what various systems, and our system is, that is what solar system, which is present in the Milky Way galaxies. We have various number of galaxies, right, and in that system we have 8 planets, right. So our planet, our own planet is Earth. So if you take, this is what, like suppose if you take Earth as a system, you know, the information, the space which is outside the Earth become like a surroundings. So that's why, what is the conclusion I am giving here means, heat flows from a body at high temperature to the body at low temperature, okay. So which can move from system to surroundings or from surroundings to system, okay. And at the same time, within the system also, it can flow, within the system also it can flow from one part of the system to another part of the system. So as simple as such, this you can say that heat transfer, no, transfer of heat, right. So heat energy flows, transfer of heat means heat energy flows from one part to another part, right, from one place to another place, from one point to another point, wherever it is, just now I told you, right. See here, heat is energy transfer from one system to another or from one part of a system to another part arising due to the temperature differences, okay, right. See, what are the different ways by which this energy transfer takes place? This is the question arises in our mind. What are the different ways by which this energy transfer takes place? That is one thing. And you know, there are 3 distinct modes. There are 3 distinct modes of heat transfer, like conduction, convection and radiation. Conduction, convection and radiation, okay, that is. Now first we are going to discuss about conduction, afterwards we will discuss convection, and at last we will discuss about radiation, okay, right. See, first conduction, first one is conduction, okay, right. See here, conduction is the mechanism of transfer of heat. I didn't write here, but I am saying, you please be concentrate. Conduction is basically the mechanism of transfer of heat between 2 adjacent parts of a body because of their temperature difference, right. I will repeat once again. He is saying that what is meant by conduction, right. Conduction is the mechanism of transfer of heat between 2 adjacent parts of a body because of their temperature difference, okay, right. Now I will tell you, I will come to the conclusion, I will come to the point of example. See, you just take one iron rod, no? So one end you are going to heat, then what happens to other end? After a certain time, after over a period of time, the other end also will become hot. See, what is the reason here? Heat energy flows from hotter end to the colder end, right? So in this example, heat transfer takes place by conduction from the hot end of the rod through its different ports to the other end. Okay, right. See, this is what happening exactly. And then gases are poor thermal conductors, while liquids have conductivities intermediate between solids and gases. Gases are poor thermal conductors. Gases are poor thermal conductors, while liquids have conductivities intermediate between solids and gases. That's I'm going to show to you in the same class. See here, I'll tell you. See, just after completion of this class, while closing this class, we will go for different values of materials. We are going to discuss about how heat transfer takes place for different materials like metals, non-metals and gases based on that physical quantity, important physical quantity, that is what thermal conductivity. Okay. So let it be. Now you look at here how the conduction takes place, that is our concentration right now. See here. See, heat conduction may be described quantitatively. Heat conduction may be described quantitatively as the time rate of heat flow. As the time rate of heat flow in a material for a given temperature difference. Heat conduction may be described quantitatively as the time rate of heat flow in a material for a given temperature difference. For a given temperature difference. Okay, right. Consider a metallic bar of length capital L. Consider a metallic bar. This is the metallic bar. Consider a metallic bar of length capital L and a uniform cross section capital A. Uniform cross section capital A with its two ends. Maintained at different temperatures. For example, it is TCM, it is what TD. Generally we are using T1, T2, no. Similarly, we used here TC and TD. This can be done, for example, by putting the ends. This can be done, for example, by putting the ends in thermal contact with large reservoirs at temperatures, say TC and TD, right? That's what we have written, TC and TD. Okay, right. Here, what is TC and what is TD means different temperatures, right? The ends which are at different temperatures, right? Let us assume, see why he is calling as reservoirs means this is like one reservoir which is at TD temperature. This is like another reservoir which is at TC temperature. It is the rod. It is the rod, right? It is the metallic bar. The gap between these two reservoirs is like L. We are going to consider mostly this part of the, right, that I will come to conclusion, that I will come to discuss. See where say TC and TD respectively. Let us assume the ideal condition. Let us assume the ideal condition that the sides of the bar are fully insulated. See the sides of the bar, these two bars are fully, this one. See the sides of the bar are fully, so there is no chance for the heat energy to come from somewhere to here. Similarly from here to somewhere. So this is what these sides of the bar are fully insulated. Okay, that is. Now see TC and TD, sides of the bar are fully insulated so that no heat is exchanged between the sides and surroundings. Okay, right. After some time, a steady state is reached. The temperature of the bar decreases uniformly. The temperature of the bar decreases uniformly with the distance from TC to TD. That is what TC is greater than TD. Here TC is greater than TD. See the reservoir at C supplies heat at a constant rate which transfers through the bar and is given out at the same rate to the reservoir at D. C reservoir and D reservoir. Okay, I will repeat once again. The reservoir at C supplies heat at a constant rate, which transfers through the bar and is given out at the same rate to the reservoir at D. It is found experimentally that in this steady state the rate of flow of heat H the rate of flow of heat H is proportional to the temperature difference and the area of cross section capital A and is inversely proportional to the length capital L Okay, right. Here capital H is equal to, see this, capital A into Tc minus Td by capital L. So capital H is equal to capital K capital A into Tc minus Td by capital L. Right. Here K is the proportionality constant. The constant of proportionality K is called the thermal conductivity of the material. That's what he is saying here, right? See, capital H is called as, right? Here capital H is called as, capital K is called as constant of proportionality. That is what capital K, which is called as the thermal conductivity of the material. Okay, right. See, it is the most important physical quantity which determines the rate of flow of heat in our discussion. That is what, through a metallic bar. And the SI unit of thermal conductivity is joule per second per m. That is what, joule per second per meter per Kelvin. Joule per second per meter per Kelvin, right? Okay. Here that is what, S. Okay. Here what is the S? So this is here. I'll repeat once again. See here, SI unit. This is very important because based on this only we are going to define. That is what we are going to define the quantity, because H is equal to K into A into Tc minus Td by capital L. You just write K as a subject. Then what will happen? HL, right? H into L by A into Tc minus Td. Okay, H into L divided by A into Tc minus Td, right? So H means what? That is, see, rate of flow of heat. Okay, so that is obviously joule, right? In that in the numerator L will be there and denominator A will be there. So L means meter, A means meter square, no, right? So meter will get cancelled. In the denominator M will be remaining. That way per meter, and it is what, temperature difference. Temperature difference means what? Per Kelvin. And initially it is what? Rate of flow of heat, no? Rate of flow of heat means what? Heat per second, heat per time. So that's why joule per second. So totally it is what? Joule per second per meter per Kelvin. And at the same time, this you can also write it as watt per meter per Kelvin. See, joule per second means that is what will come, no? See, what is that word? Power. Power is equal to work done by time, right? That's why joule per second you can replace with watt, right? Watt per meter per Kelvin also you can write as a SI unit of thermal conductivity. Okay. Now this physical quantity is very important, not only for board, for NEET point of view also, which is very important. Okay, right? Now the values of thermal conductivities varies slightly with temperature. The values of thermal conductivities changes slightly with temperature, but can be considered to be constant. Over a normal temperature range. Okay, right. And now I am going to discuss some of the applications, some of the importance of thermal conductivity. You please be concentrate. See, for example, if you take relatively large thermal conductivities of the good thermal conductors, for example, the metals, with the relatively small thermal conductivities of some good thermal insulators such as wood and glass wool. Okay, you may have noticed that some cooking pots, we have seen some cooking pots have copper coating on the bottom. Am I right? Because copper is a good conductor. Being a good conductor of heat, copper promotes the distribution of heat over the bottom of a pot for uniform cooking. Okay, right. Next, plastic foams on the other hand. Plastic foams on the other hand are good insulators. Plastic foams on the other hand are good insulators. That is what, mainly because they contain pockets of air. Okay, right. Recall that gases are poor conductors. And note the low thermal conductivity of air. In this table, what is the thermal conductivity of air? Which is 0.024. Okay, right. And you can also see from the table, heat retention and transfer are important in many other applications, right? See, in this table you can see thermal conductivity of different materials, see, metals, non-metals, gases, okay, that and all you can see. And one more important point, retention of heat retention and transfer are very important in many other applications, right? For example, houses made of concrete roofs get very hot during summer days because thermal conductivity of concrete, though much smaller than that of metal, but is still not small enough. See here, concrete, how much the value, right? So concrete, the value will become 0.8 concrete, it will be 0.8, right? So 0.8 thermal conductivity means it is almost high enough. That's why in summer even we can't sit comfortably, we can't live comfortably in the roof, right? In the concrete roofs, the houses made of concrete roofs. Okay, that is next. Therefore, people usually prefer to give a layer of earth. Or foam insulation on the ceiling so that heat transfer is prohibited and keeps the room cooler. I think you may have experience, especially when the time comes regarding the summer, the peoples used to coat on the roof of the concrete building. What this roof, if you see that coating, what the role of this coating means. See, whatever the heat which is going to incident on the roof, it will reflect back into the atmosphere so that the inside of the concrete building, what is there, will keeps at low temperature, will keeps at cool. That's what I can say. That is what example to the daily life. Next, in some situations, in some situations, heat transfer is critical. For example, in a nuclear reactor, for example, elaborate heat transfer systems need to be installed so that the enormous energy produced by nuclear fission in the core transits out sufficiently fast, thus preventing the core from overheating. See, it is a very important application as well as very dangerous thing also. That is what nuclear reactor. Because of the nuclear reactions taken place in the nuclear reactor, okay, see, enormous amount of heat will be released. To bear such amount of heat energy, the walls of the container are very high, very much thick. Even though these are very much thick, there is a capacity, there is a bearable limit regarding the heat energy by that particular thick walls. If the heat is more than that, what will happen? Obviously, it will melt. That's why there is a mechanism. Which prevents the core from overheating. That is the only thing which can prevent. Otherwise, what will happen? If there is no such mechanism, means the nuclear reactor will, the walls of the nuclear reactor will melt, and there is a collapse of nuclear reactor, and it is very highly dangerous because in that surroundings, radioactive substances are there, right? So, which are very harmful to the human health, not only for human, which emits very dangerous radiation. That is what releases energy in the form of radiation, right? So with that energy, with that radiation, we are going to get so many diseases like cancer and right, skin allergies, and that is what skin cancer, okay, lung cancer, etc. That's why we have to prevent that overheating mechanism in case of nuclear reactor. That is what very, very important thing. Okay, right. And now you can see thermal conductivity values for different materials, right? For metals, non-metals, and gases. For metals, if you take metals, for example, silver 406, copper 385, aluminium 205, brass 109, steel 50.2, lead 34.7, mercury 8.3. See, based on these values, you can understand where we are using silver, where we are using copper, where we are using aluminium, where we are using brass, where we are using steel. Similarly, where we are using lead, where we are using mercury. Generally, mercury we are using in thermometers, no? That is, right? See, aluminium we are using for, that is what, transfer of electrical energy from one place to another place, no? High tension wires, HT wires. Similarly, copper, right? Copper, just now I told you one important application, that is what, cooking vessels. Cooking vessels, the bottom of the cooking pot made up of copper, because the distribution of heat is very good in case of copper. At the same time, copper is a good conductor of heat also. So based on these values, see, silver is 406, but mercury is 8. Sorry, silver is 406, but mercury is how much? Mercury is 8.3. Mercury is 8.3. So once imagine how much difference is there between the silver and mercury, right? As I told you already, gases are the bad conductors of heat. Once you see here, air 0.024. See the silver 406. See the copper 385, right? So 385 is the thermal conductivity of copper when compared to air 0.024. So that you can say confidently, no? You can say confidently gases are the bad conductors of heat. Okay, right. But non-metals, that is those are like intermediate between metals and gases. Say for example, if you take insulating brick, that is 0.15, concrete 0.8, body fats 0.20, felt 0.04, glass 0.8, ice 1.6, glass wool 0.04, wood 0.12, water 0.8. Okay, see, if you see the glass and water which have the same value of thermal conductivity, that is 0.8, and if you compare the non-metals within themselves, right, and felt, right, and body fat, felt has very least value, at the same time glass wool also least value. After that, high value in case of non-metals is what? 0.8, right? Sorry, 1.6, ice is there. 1.6 is the highest value in case of non-metals regarding thermal conductivity. Afterwards, gases, air 0.024, argon 0.016, and hydrogen 0.14. Hydrogen 0.14. Okay, so these are the values of thermal conductivity for different materials, like metals, non-metals, and gases. Okay, that is. So what I am saying here is, in this class we discussed about heat transfer. See, the name itself indicates heat transfer means the energy of the heat energy moves the heat energy transfer from one point to another point, that is from either from one system to another system, or within the system from one part of a system to another part of system, due to the temperature difference. Temperature difference is kandipa. Okay, Q is equal to ms delta T. Q is equal to ms delta. When there is no temperature difference, so there is no flow of heat energy, no. That is what, when there is no contact from system to surroundings, that's what I am saying. Okay, right. So that is what. But heat transfer takes place in three modes: conduction, convection, radiation. Okay, but in this class mostly we concentrated to discuss what is conduction, right? So if you take a metallic bar of any length, you know, if we heat one end of the rod, the other end also will become hot after over a period of time, because of, right, because see, a rod means that is the combination of molecules, no, right. See, if you are going to heat one end of the rod, the heat energy will be exchanged, will be transferred by receiving one molecule to the neighboring molecule, to the neighboring molecule, to the neighboring molecule, and so on, right. This is the way of transfer of heat. So without changing the position of molecules, without changing the position of the molecules, the transfer of heat takes place from one part of the body to the another part of the body. That is what you can call it as conduction, right. Here itself we got a new physical quantity and important physical quantity also, that is what coefficient of thermal conductivity or thermal conductivity, that is what capital K. So H is equal to Ka into Tc minus Td by capital L. H means rate of transfer of heat, rate of flow of heat, and K is the thermal conductivity, and A is the area of cross section, Tc minus Td is the temperature difference between the two reservoirs in this activity, and L is the length. Okay, this is the L. Okay ma, right. So like this you can discuss about thermal conductivity, and in this table we have some values of thermal conductivity for different materials like metals, non-metals, and gases. Okay, based on this table you can conclude the usage of different materials in different practical applications. Okay, that is right. Okay ma, thank you. In the next class we will continue with next continuation example problems 11.6 and 11.7. Thank you.